Good afternoon, everyone. My name is Mjed Hashem. Today I'll be presenting my master's thesis defense presentation on the laser-based pretreatment of secondary bonded composite T-joints for improved energy dissipation. So for the outline of the presentation, I'll start with the introduction, followed by a short literature review. Then I'll go through the aims of the study, and then I will discuss and present the manufacturing characterization techniques, and then the results and discussion following the conclusion and the future work. So as you may be aware, composite materials, namely carbon fiber reinforced polymers, have been widely used in the aerospace industry, mainly due to their high strength and high stiffness compared to low weight ratio. For example, in the Boeing 787 Dreamliner aircraft, 50% of the aircraft is composed of advanced composites, 50% by weight. And in this aircraft, there are other components inside the aircraft structure, which actually requires many connections between those components. So for example, if we look at the wing, inside the wing, there are the ribs and the spars, the front and the rear spars, and there are the stringers and the skin. And metallic components are actually used, and bolting and riveting of nuts is employed in such applications to connect these components together. However, this has a huge weight penalty and high stress concentration where the bolting and riveting is happening. So therefore, T-shaped composite joints are used or can be used in such applications to stiffen and connect those structural components. And the advantage of those T-joint structures is that the geometry allows the stresses to be distributed and transferred from the stiffener to the skin without the need of bolting and riveting. And the main components are two laminated stiffeners bonded to a skin using a special adhesive. However, the quality of this bonding determines the integrity and durability of those T-joint structures. So here is a typical illustration of a T-joint structure. A T-joint structure is composed of a stiffener, which is the L-shaped structure here. So two stiffeners connected to each other or bonded to each other using a special adhesive. And they are all bonded to a massive skin on the bottom, which is the larger part on the bottom. The top part of the stiffener is known as the web, and the bottom part is known as the flange. And the curvature region is known as the radius bend region. And this is the region which experiences the highest amount of stress concentration, while the center is known as the delta fillet or the noodle adhesive region. And this is where the cracks usually initiate from. So typically in T-joint structures, there are two different toughening or toughness tests involved. The first one is a bending test where a monotonically increasing load is applied perpendicular to the stiffener. So the stiffener is actually held sideways and the load is applied perpendicular to the stiffener. The second mechanism or the second test is a tension test, which involves having a boundary condition where the skin and the stiffener are clamped on the bottom and the load is applied in tension in the same direction of the stiffener. So for this study, I will focus mainly on the tension. I'm not going to go over the bending. The preliminary failure techniques or the failure mechanism in T-joint structures depend mainly on the boundary conditions and on the manufacturing induced defects. So there are four main preliminary failure mechanisms. The first is the debonding between the stiffener fillet interface, which is when the cracks are actually initiating at the interface between or at the interface in the delta fillet region. The second is the delamination between the stiffener plies, where the cracks are actually moving inside the plies of the stiffener. And this can also be attributed to the manufacturing defects between these plies. The third mechanism is the debonding of the flange tip from the skin. So when the cracks actually initiate at the edge of the flange skin interface. The fourth mechanism is the debonding at the fillet stiffener intersection, is when, according to a certain boundary condition, the cracks are propagating vertically upward in the T-joint structure. Further, there can be different failure mechanisms in T-joint structures, depending also on other conditions, such as waviness of the plies or insertion of foreign objects. Therefore, there are many toughening techniques in the literature. I'll highlight the main ones. So the first toughening technique is modifying the geometry of the T-joint structure. And this can be done by modifying the delta fillet or the curvature region here to improve the impact resistance. So this is mainly applied in marine applications such as boats or naval applications to resist high wave impact. This is only limited though to certain applications where such geometrical modifications are allowed. Second mechanism is by employing bio-inspired designs. These designs are usually inspired from the animal or the bird bones, and this is actually practically done by inserting a foam in the region between the plies of the stiffener. And this insertion of foam or this bio-inspired design provides an improved damage tolerance. However, this again has a limitation, and this limitation here is the onset of damage initiation earlier. A third toughening technique is by using stitching or Z-pinning. So pins or stitches are actually placed to improve through the thickness strength in between this interface of the skin and this stiffener. However, this requires requalification and high material cost and can incur weight penalties. Another toughening technique, which is not mainly modifying the structure of the T-joint, but rather the adherent themselves, is by applying a pre-treatment on the adherent. So in T-joint structures, the adherents would be the skins and the stiffener interfaces. And there's a study that showed how abrasion and peel ply demonstrate as compared to untreated T-joints. So in this study here, maximum loads have been recorded in tension, and it was noticed that abrasion produced the highest amount of load resistance as compared to untreated and peel ply treated, where peel ply was the lowest. Another interesting fact about the study is they studied where the crack initiated in their case. So in their case, the crack initiated at the edge of the T-joint and then moved towards the center. And SEM images has been taken at the edge of the T-joint and as well at the center of the skin. So SEM images has been taken of the skin. And those images showed that there are at the tip where the cracks actually initiated at, or where the failure begun at, there has been some scarps and river lines. And these are indicators of mode 1 fracture toughness, mode 1 toughness. Mode 1 failure. And mode 1 failure is the opening mode. So at the center of the skin, serrated feet and cusps have been noticed, which are indicators of mode 2, the sliding mode failure. So therefore, we can actually assume that there is a mixture between mode 1 and mode 2 during the complete failure of T-joint structures. Initially, recently there has been some application of carbon dioxide laser irradiation, which produced surface conditions similar to that of abrasion in single lap joints. Also locally in the KAUST laboratories, there has been studies on the effect of CO2 laser irradiation to improve the toughness of mode 1 and mode 2 bonded joints. So in double cantilever and in end notch flexural tests. And their improvements can be contributed to phenomena known as adhesive ligaments and fiber bridging and secondary cracks in the adhesive. Therefore, I thought of applying this CO2 laser irradiation, which produced improvements in mode 1 and mode 2, and produced results similar to abrasion, applying this into T-joint structures. So the objective of this study or the research is to investigate the effect of CO2 laser pretreatment on the toughness and the safety of CFRPT joints, and understand the failure mechanisms in those toughened CFRPT joints, considering different surface ply orientations. Sorry. I'm also going to understand the influence of the interface ply orientation on the response of laser-treated surface T-joint. So in my study, there are 4 different pretreatment techniques. The 4 pretreatment techniques include peel-ply pretreatment, which is a baseline fabric pretreatment. The second pretreatment technique is a laser cleaning, which is a low-fluence laser irradiation of carbon dioxide. The third pretreatment technique is a laser ablation, a uniform laser ablation, which is a high-fluence laser pretreatment, and a laser patterning, which is an alternation between laser cleaning and laser ablation. The stacking sequences will involve quasi-isotropic stacking sequences, which will, four designs will involve having a 0-degree surface fiber at the interface, and 2 extra designs will involve having a 45-degree surface fiber at the interface. This will be applied to laser ablation and laser patterning. So in terms of referring to the T-joints, I refer to PP as peel-ply and laser cleaning as LC, laser ablation as LA, and B5G5 as patterning. The ones which had a 45-degree surface ply had LA45 and B5G5-45. So just to illustrate how the pretreatment or the laser pretreatment will be applied, the laser pretreatment was applied to the interface between the flange and the skin. So it is this bottom region here of the flange and the top part of the skin, which are bonded together using the adhesive. And the pretreatment involved, as I said, the laser patterning, which was the alternative pattern between LC-LA, or a full uniform laser ablation or full uniform laser cleaning. So for the laser patterning, the parameters which was taken from the name B5G5, they have been taken from a previous study, which optimized that, or which concluded that these parameters are the best parameters that produced the best toughness in mode 2 end notch flexural test. So it was taken by leaving a gap of 5 millimeters and taking a width of LC of 5 millimeters. And the area which was treated was 110 by 100 millimeters squared. And the gas used was carbon dioxide, which had a wavelength of 10.6 micrometers. The LA power was 30%, and the LC power was the LA power is 30%, and the LC power was 10%. Sorry. So for the manufacturing of the T-joint structures, secondary bonding manufacturing technique was followed, where the stiffener and the skin was manufactured individually, and each side of the stiffener was manufactured individually as well. So let's start with the manufacturing of the stiffener. A mold was designed previously, which was covered then with a peel-ply fabric from one side and a breather fabric from the other side. And the CFRP prepregs were laid up on they were laid up by hand on the mold with the respective quasi-isotropic stacking sequence. They were rolled over with a roller to ensure there are no air entrampments between the plies, and they were inserted once 8 layers of CFRP prepregs were stacked. Once the 8 layers are stacked, the mold was closed and it was locked with some bars and was inserted into the oven. And in the oven, they were heated for 2 hours at 180 degrees under vacuum of 25 inches of mercury. After the T-joints have been cured, they were removed. The peel-ply was removed, and this was considered to be the peel-ply treated T-joints. Just want to highlight before I move on that all the T-joints, whether they were peel-ply or whether they were laser treated, they all experienced a peel-ply treatment when they were manufactured. So for the skin, the manufacturing technique was different, and the manufacturing technique followed a hot press method, where a metal mold was actually covered with a Teflon sheet, and then this Teflon sheet was covered again with a peel ply fabric. And the CFRP prepregs were laid up. This time, 16 layers of the prepregs were laid up with the same respective quasi-isotropic stacking sequence, and then they were covered with the breather sheet, and then a silicon seal and vacuum bag was on top of everything of the mold. And a vacuum pump or a vacuum source was on insert, and this mold was inserted then to the hot press machine, and they were cured in the hot press machine with a force of 63 kilonewtons and I'm sorry, with a force of 30 kilonewtons and temperature of 180 degrees Celsius for 2 hours. And the cured skin was also produced. And then once the cured skin and the cured stiffener were cured, they were cut, and then they experienced the laser treatment. So these are images of the skins and the stiffeners after the treatment. We can notice here that there are some alternation between a dark region, which is the LA, and a lighter region, which is the low fluence laser cleaning LC. The laser patterning was also applied to the stiffener. And on the right, we have the pure or uniform L8 pretreatment. Once they were laser treated, once the skins and the stiffeners were laser treated, they were secondary bonded using an Earldite 420 AB adhesive, and they were cured. I just want to highlight here that the mold is actually flipped this time, because we wanted to ensure that there are no air entrampments or no voids inside the adhesive. So they were flipped and they were bonded together and inserted into the oven, and they were cured for 3 hours. The first 15 minutes under vacuum, and then they were cured for 3 hours at 60 degrees. Once the adhesive cured, the T-joints were cut using a water jet cutting machine and a diamond cutting machine. And the dimensions of each T-joint produced is shown here. It is worth highlighting that the length of the T-joint was 230 and the width was only 25 millimeters of each T-joint specimen. After the T-joints have been manufactured, they were mechanically tested through what is known as a stiffener pull-off test. So in the stiffener pull-off test, a universal testing machine has been optimized, which simulated tension. And then a camera was used to take images of the in situ damage analysis, or the in situ damage. And the fixture was actually designed previously by me, because I'm actually the first one in the lab or in our center to work on Tjoint structures. So we had to design a specific fixture using the SolidWorks, and then the pull-off test actually simulated real-life conditions of internal pressure on the fuselage skin, for example. The delamination was expected to occur at the interface between the skin and the flange, because this is the area where the strength is the lowest. So for the results and the discussion, let us start with results before mechanically testing those T-joints, or before the tension happens. Sorry. So the skin, just to illustrate the effect or the impact of the different pre-treatment techniques I applied. So the skin was treated with a peel ply and LA and LC, and surface profile morphologies has been analyzed using a surface profilometer. And what we noticed out of the results was that the peel ply and the LC produced high fluctuations on the surface profile. And these are indicators of contaminants or contaminations on the surface of the peel ply and the laser cleaning. While the LA produced a low surface profile with not many fluctuations as compared to the LC or the LA. And this is mainly due to the full exposure of the fibers and the removal of epoxy off the surface. It is worth noticing that at the interface between LA and LC, there is a high change in the surface morphology, and this can be an area of interest because this can be an area for the crack to arrest at, because when the crack is moving in the LA and then it faces a huge change in the morphology height, it would be difficult for the crack to propagate further, and it would require more energy. So this can be a cause for the for the cracks to arrest. A limitation of this scanning technique, or this topology analysis technique, is that the profile scans are limited by the finite size of the tip of the stylus. So as we know, the fibers of the carbon fiber can be 7 microns or even smaller, maybe 5 microns. So, and the distance between the fibers can be even smaller. So it might be difficult to get accurate scans, which can justify why there are some peaks appearing in the LA. Moving on to scanning electron microscopy imaging. So the SEM images was again taken at the interface between, were taken at each pretreatment. So the purpose of this imaging is again to illustrate the effect of the pretreatment technique, and this is before the failure, as I highlighted earlier. So we can see here that there are the p-apply pretreatment, and we can see some particles on the surface. Similarly, in the LC, we can see the same particles or very small exposure, if any, of the fibers. However, in the LA case, we can see the fibers fully naked and fully exposed. And it is worth noticing that there are some fiber cuts here and here in the 0 direction. However, when we analyze the SEM images of the skin, which had a 45-degree fiber direction at the interface, we notice that there are, with the p-apply, there are areas of imperfect wetting, or there are areas of exposure of fibers as compared to the other ones. And this is mainly due to the removal of p-apply with 45 degrees. So p-apply fabrics are removal is a manual process, which can be quite difficult to achieve, or requires requalification and labor. So if the p-apply was not removed in the same direction as the fibers, then such phenomena can occur. A second point to highlight here is that with the LA45, the fibers were not cut. And the difference between the LA and the LA45, why did the cutting happen here and did not happen here, is because the laser tip was actually moving in the same direction as the fibers in the 0 direction. So the laser tip was moving in the 0 direction, and the fibers were also in the 0 direction. And this allowed the fibers to accumulate heat and cut. While in the 45 degrees, the laser was moving in the 0 direction, and the 45-degree fibers were able to cool down by the time the laser came back again. Moving on. So after the T-joints experienced the mechanical tests, I will demonstrate now the results that was achieved. We can notice that the first graph here, it is illustrating the p-apply pre-treated results. We can see that there is a sudden brittle failure at the p-apply pre-treatment. And this happened at very low loads and very low extensions. As compared to the LC, which was the laser cleaning, we can notice that there was some improvements with laser cleaning. There are some minor peak drops, and the failure happened at higher extensions and higher loads as compared to the p-apply. Moving on, the LA pretreatment produced even more peak drops as compared to laser cleaning. Sorry, the failure also happened at a higher load and a higher extension as compared to both LC and LA. Finally, the patterning, or the B5G5 pretreatment with the 0-degree fibers. By the way, all those 4 curves over here are of 0-degree fibers, so on the surface. So the patterning provided even much better results as compared to the other 3 pretreatment. And we noticed that the failure started transforming into progressive failure rather than having catastrophic sudden failure with the P-ply. And to notice how the T-joints would change when we change the surface fiber direction, we can analyze the results by looking at how, for example, a 0-degree patterning can compare with a 0-degree or can compare with a 45-degree patterning. We can see that the area under this curve is almost doubled when it was switched from 45 to 0. So the blue dotted line here, or the blue dashed line, which indicates patterning, B5G5 with the 0, produced a higher average critical displacement as compared to 45, and also a higher average maximum load as compared to 45. This was also confirmed with LA. So if we consider LA 0 degrees with LA compared to LA 45 degrees, we can notice that the LA with the 0 degrees produced enhanced toughness as well. So if we were to compare the baseline P-ply design, which was the weakest, we will compare it with the B5G5, the strongest or the highest toughness T-joint. We will notice that the load almost doubled. The maximum load almost doubled from 788 to 1,712, more than doubled actually. So what was the mechanism which resulted in this enhanced toughness? We had to, okay, so just before I go to that point, let me illustrate the energy dissipation. The energy dissipation was calculated by finding the area under the load extension curves. And again, similar to the maximum load and the average critical displacement, the energy dissipation was largest with the B5G5. And this improvement was recorded as 12 times higher than P-ply. And when the fibers were switched to 45 degrees, it was only 6 times higher than P-ply. So the energy dissipated, as I said, the area under the curve almost doubled when moving from 45 to 0. And to look at why the 0 degrees patterning provided an enhancement in the toughness, we analyzed the images taken during failure, and we noticed what is known as an adhesive ligament. So an adhesive ligament is when the crack propagates and it stops for a certain reason, and then it initiates from a different regime or a different region. So as we can see here, there's a first adhesive ligament that happened. Following, a second adhesive ligament happened here, and then the third here, and then the fourth was the final one that happened here or here. After the fourth adhesive ligament failed, the fourth adhesive ligament met the first adhesive ligament, and sudden failure happened for the T-joint. So to analyze or to relate those adhesive ligaments to the load extension curve, which resulted for the specimen, we can actually relate each adhesive ligament with a peak drop. Or if I may say, we can relate it with an enhanced toughness, an increase in the extension of the T-joint. And there has been 4 adhesive ligaments, as I said, and when the fourth one failed, the sudden failure happened. So we can look at this video here. We can see that the adhesive ligaments first initiated here, then at the edges. And then when the adhesive ligaments were completely failed, sudden or progressive failure happened, indicating, let me play the video one more time. Okay. Sorry. So when the adhesive ligaments happened, they resulted in enhanced toughness, and that indicated a safer T-joint. As compared to P-ply, if I was to show a video of a P-ply failing, then the failure would not even be recorded. The cracks would just propagate really quickly, and sudden failure will happen, or catastrophic failure will happen. So to analyze the failure mechanisms that happened, visual and CT imaging has been taken, and it was noticed that for the P-ply pre-treatment, an interfacial failure happened, such that the crack propagated at the interface between the adhesive and the substrate, or the adhesive and the skin in this case. For the LA, LC, B5G5, LA45, cohesive failure occurred, or a mixture between cohesive failure and interfacial failure. So I explained what interfacial failure is, and cohesive failure is when the crack propagates inside the adhesive, and this results in adhesive present on both sides of the skin and the stiffener. For the B5G545, that one is the patterning with 45 degrees at the surface. A different failure mechanism happened, which was a substrate failure, such that the crack entered the substrate of the skin and detached fibers of the skin. So this was verified using a CT imaging, and I noticed that the crack propagated at the interface and then entered the skin, propagated inside the skin, and then went back into the interface. And this resulted in an increase in the energy dissipation as a non-local damage mechanism happened in the 45 degrees. However, this was not as high as an improvement produced with the B5G5 adhesive ligaments illustrated earlier. So if I was to relate the laser patterning 45-degree load extension curve to the substrate failure that happened, we noticed that when the crack entered the substrate, this resulted in a huge extension through the skin. However, after it propagated out of the skin, sudden failure happened. And we can analyze the two different mechanisms of failure that occurred in those T-joint structures which were patterned or which experienced a laser patterning. So in the first case scenario, which was the 0-degree fibers, the phenomena of adhesive ligaments were created due to the patterning at the interface between LA and LC treatment. And this ligaments allowed the crack to migrate between the interface and the adhesive, increasing the energy dissipation. However, there has been a different phenomena that occurred with the 45 degrees, which is known as a coupling edge effect. So as we know, the stress concentrations are very high at the edges at the free edges in general. And in this case, the 45-degree fiber direction increased the stress concentration at those free edges, and it was really easy to peel or remove the fibers off the skin. This enhanced or allowed what is known as substrate failure to occur with the 45 degrees. And analyzing back the crack, as the crack entered the skin, it stored a huge amount of energy. And the energy release rate of the crack was really large, that as soon as it exit the skin or it exit the substrate, it was larger than the toughness of the T-joint, and this allowed sudden failure to occur. So in conclusion, the laser pretreatment technique provided enhanced toughness and energy dissipation as compared to P-apply. The laser patterning resulted in up to 12 times enhanced energy dissipation through the activation of non-local damage mechanisms such as adhesive ligaments and substrate failure. Progressive failure was recorded for laser pattern T-joints. However, catastrophic failure occurred with P-apply treated T-joints. And this indicates that a safer joint can be produced using the laser patterning pretreatment. Finally, the ply orientation on the surface has a significant effect on the stress distribution and the failure mechanism, such that the T-joints that was patterned with 45 degrees on the surface showed 6 times enhancement in the energy, while the patterned with the 0 degrees showed 12 times enhancement in the energy. Just before I close my presentation, I would like to go through my future work, or share with you my future work. So currently I'm publishing a paper on the laser-based pretreatment of secondary bonded composite T-joints. This is the work I'm presenting today. I'm also planning to participate in future potential projects involving the insertion of sacrificial cracks inside the adhesive of T-joints to enhance the toughness, and or applying 3D patterning techniques in the enhancement of secondary bonded adherence. And a potential project which is interesting for me is applications of composite materials in oil and gas industry, applications, such as pipelines and similar. I am also going to present and participate in the KAUST Future Composites poster competition, which will take part between May 24 and May 27 of this year. And I'd like to invite you all to attend this workshop by registering on the following website. Finally, I'd like to acknowledge and thank my committee, Professor Jill Libinu, my principal investigator and my academic advisor in this work, who has been an excellent professor in terms of both the academic and the research level. And I really learned a lot from him. I'd also like to thank Dr. Ahmed Waji, who has been my direct supervisor or mentor on this project, who is a postdoctoral fellow in Dr. Jill's or Professor Jill's lab. I'd also like to thank both Professor Frederick Lacoy and Professor Thomas Anthopoulos, for who I've actually taken classes with, and I really enjoyed for attending this presentation and for their insightful comments and feedback. Finally, I'd like to thank my colleagues at the Composites and Heterogeneous Material Analysis and Simulation Laboratory, KOHMAS. Namely, I'd like to thank Dr. Ran Tao and Dr. Arif Yudanto. I'd like to also acknowledge the competitive research grants at King Abdullah University of Science and Technology for funding my studies and funding my research. My appreciation also goes to my family and friends and everyone who supported me in this journey. Thank you for your questions and thank you for listening.